All right, so welcome back. We've covered solids and liquids so far. And just a quick review of what we've learned so far. We said that in a solid, particles were tightly connected. And one of the key ideas of the kinetic theory is that as you heat something, the particles move faster and faster. Or the opposite is true, as you cool something, the particles slow down. So at some point, the particles in the solid, as you're heating them, they're moving so fast and they're vibrating so much that they start to tear the bonds that hold them together as a solid apart. And then they melt and become a liquid. At some point, as the liquid is heated, the particles are moving faster and faster, and those connections that we saw in the last video that were still there holding the liquid together, eventually the particles are moving so fast that they completely break those last bonds and they become a gas. Because there's nothing connecting them anymore. There are no bonds remaining. They have no definite shape. They have no definite volume. That means that the gas will take the shape of its container. So if you put air in a basketball or air in a tire, it takes the shape of its container. It can also, though, change size. It can change volume. As I just explained, the particles have completely overcome all of those attractive forces that were holding them to the other particles, and now they are completely free to move independently, far from the other ones. So they're going to spread far apart, and they're going to fill all of the space available to them. Remember, those particles are in constant motion. They're completely not connected. So I put 5 particles in our container over here, 6 particles. And it shows they're moving in all random different directions. Okay? Particles have so much energy that they've broken all the bonds. Unlike in the other diagrams where the particles were still connected someplace, these have no connections. Because they have no connections, they can do some special things. They can expand and contract. So I got our 6 particles here in this little container. And if we move them over to this container, they will expand and fill all of this space. If this is like a bicycle pump, it's going to take the air in the pump and it's going to squeeze it down and put it into the ball or the tire or wherever you're putting it. So the gas particles can also be squished together and they can contract. When you let them loose in this bigger container, when they spread out and take up all the space available to them, that process is called diffusion. So just like last year you learned about when things diffuse in a cell, it's the same process. It spreads out. But just like any of these things with the kinetic theory, when you heat them, the atoms move faster. And they move slower when they're cooled. The boiling point, or vaporization point, is the temperature at which a liquid particles change into a gas. And just like when we had the energy that was required to rip the bonds apart so that a solid could become a liquid, that was called the heat of fusion. The energy necessary to rip the bonds apart that were holding it together as a liquid, so it had that definite volume, to break all those bonds apart so that it becomes a vapor, is called the heat of vaporization. Now, some of you may have heard of plasma. Plasma is a state of energy consisting of a high temperature gas, so we've heated it even more. And it's become charged. So what's happened is it's gained so much energy that it's really described as a state of energy stripped of its electrons. So the electrons have a negative charge and the protons in the nucleus have a positive charge. So when the atom loses the negative electrons, it becomes a positively charged nucleus is basically all that's left. It is not common on Earth. Okay? However, it is the most common state of matter in the universe because stars are made of plasma. So I brought up a picture of our solar system. Okay? This is not the way the planets are arranged around the sun, but it does show the relative size of the planets. So this is proportional. So Earth is teeny, teeny, tiny compared to the sun. The sun is ginormous. You could take all the other planets and stick it inside the sun and still have tons of room left over. So when we say it's the most common in the universe because stars are made of the sun, stars are made of plasma, it's the most common because look at the size of the sun compared to everything else. On Earth, we see plasma and fire and lightning, and then, of course, it's on the sun. Thermal expansion does exactly what its name says. Thermal is heat, and things expand. So, like we've learned before, as the particles move around and they're vibrating faster and faster, when they're cold, they're not vibrating much and they're not taking up too much space. And as they start to heat and they vibrate faster and faster, they're taking up more space because they're moving farther away from each other, so the substance starts to expand and it gets bigger. So I put heat over thermal, so you can really think heat makes things expand. Okay, and the word we use is thermal, but thermal and heat are pretty much synonyms. And then the opposite happens when you cool a substance. Okay, the size of a substance will decrease when the temperature decreases. So if you cool it, it'll get smaller. So if you think like in the wintertime, if you go and buy one of those balloons at the grocery store, and in the store it's all blown up and it's full size, and you take it outside where it's really cold, it gets smaller and it looks like it's deflated. But then if you bring it back inside where it's warm, the particles heat up and they gain energy and they take up more space and the balloon fills back up. Now, there's 3 examples of thermal expansion that I want to show you. One of them is they're going to show you what happens, how it decreases size when it cools. One of them, we're going to take a look at what happens when they heat the same objects and it expands. And then the last one is a real-life example of thermal expansion and why you need to pay attention in school. After we look at those videos, I want you to answer the questions for section 2 that are the remainder of this page. So what are 3 parts of the kinetic theory down to those 2 tables at the bottom of the page you need to fill out yourself. And we'll pick this up next time. So this is a short video clip that I wanted to share with you on thermal expansion. So we said as you heat the particles in something, they move faster and they take up more space because they're vibrating, and the faster they vibrate, the farther away they move from each other. Okay, in this case, they're going to cool it down, so the ring got smaller because the particles are vibrating less quickly, and now the piece of brass won't fit through the ring because these particles, where they had stuck it in the liquid nitrogen, are moving so slowly they got closer together because they're not vibrating very fast, and they take up less space. Okay, now this next video, they're going to do exactly the opposite. They're going to heat the ball, the brass knob up, and then see if it fits. Okay, so they hit the brass out, they heat the brass alloy, and it easily fits through there. Okay, because the particles are moving faster, and the faster they move, the bigger it got. Now they're heating the other piece up, so the particles in that brass knob are going to be moving fast. It should get big, and it's too big to fit through the brass ring now. That's because it expanded in the thermal expansion. Share with you is a real-life example of thermal expansion. When I saw this article on the BBC, it says, teenager stomach removed after drinking a cocktail. And what they're doing here is they're putting liquid nitrogen in glass, and then what you're supposed to do is pour it into your drink, and then because liquid nitrogen has a boiling point of like negative 300 degrees, as soon as it it's mixed in, it starts to boil. And because it boils really, really fast, it just makes a lot of bubbles, and then it's kind of like frosty freeze. So like the drink is kind of like frosty freeze. Well, this girl drank the liquid nitrogen instead. Now, this reeks of like I didn't pay attention at all in school, so I did some really stupid stuff. You guys all know from this unit that when the liquid, where the particles are held close together, boils at negative 300 degrees, and so your body is way warmer than that. Not only is it going to boil and turn to a gas, and a gas takes up a whole lot more space, but it's going to be a warm gas because it's going to go up almost 400 degrees in temperature. It's going to expand, and that's just what it did in her stomach. It boiled, and then it heated, and it expanded, and it blew her stomach up. So it said the teenager has to have emergency surgery to remove her stomach after drinking the cocktail. And she was diagnosed with a perforated or pierced stomach and is now in serious but stable condition. Perforated or pierced means, this is a nice way of the article saying that she blew her tummy up. So you need to pay attention in school and learn about thermal expansion so that you know you don't drink liquid nitrogen if you don't want your tummy to explode.